Good morning, students. In the last class, I taught about how to make high temperatures, in order to make solid state materials in ceramic form or melting of alloys and metals and fusing them into alloys, or making intermetallics. Ceramics and intermetallics are, of course, line phase compounds. High temperatures are required, and there is no single solution to produce high temperature. There are some materials that require medium range temperatures for heating up to 800 to 900 degrees centigrade. Some materials require temperatures up to 1400 degrees centigrade, and some refractory elements, if they are used to make compounds, you need much higher temperatures as high as 1800 degrees centigrade. And even some of the ceramics, like involving zirconium oxide and aluminum oxide, have very high melting points, and ceria, for example, cerium oxide, cerium dioxide. You need real high temperature furnaces. I also mentioned that it's very common to use certain heating elements at the lab level for regular heating of compounds, like nichrome, kanthal, silicon carbide, that can take you all the way from 800 to 1600, 1700 degrees centigrade. Super kanthal, that is molybdenum disilicide rods, can be used to realize temperatures of the order of 1800 degrees centigrade. But of course, I also mentioned that molybdenum disilicide rods are very expensive, even for that matter, silicon carbide, because you're taking these alloys like nichrome or kanthal and semiconducting compounds like silicon carbide or molybdenum disilicide through a number of heating cycles. You're heating the compound in a furnace using these heating elements up to 1000, 1200, 1400 degrees centigrade. You're cooling it back. Again, the next heating, the third heating, the 100th heating. So you're continuously making these heating elements to go through thermal cycling, which means in a normal box furnace where there is no special atmosphere, air is always present, there's every possibility of these rods getting heated up. And that can change the resistance of these wires in a big way. So you need to replace these rods, depending on the usage. That means a nichrome wire, which doesn't have any oxygen in it, starts getting oxidized. The surface oxidation, which then goes to the depth of the rod diameter. And you can imagine if 1/4 of the rod material is converted into an oxide, you'll start seeing changes in resistance. And so you need to pass different currents to achieve high temperatures. Sometimes when the resistance changes drastically, achieving the required temperatures using that particular set of heating elements is not possible. So all these things have to be taken into consideration. And then I mentioned about how to make these intermetallics, or fusing of alloys. Fusing of alloys and intermetallics require furnaces that produce very high temperatures. So normal resistance heating furnaces are not useful. So in that case, what do we do? Typically, there are two things. One is heating these metals to make alloys and intermetallics. require high temperatures and also inert atmosphere. So I described about how arc melting furnace is used. It's a small container which is evacuated, and you generate a plasma by striking a plasma between two electrodes. One electrode is the one on which the melting happens. The other one uh, is a uh, mobile electrode, and how we produce plasma. Plasma is produced after evacuating that small chamber. You have argon gas inside it, so it's argon plasma that is quite hot. And since it is quite focused, because you're using a pointed electrode, you see the plasma there, like here, what you see here, in the form of that light there, and that'll it's of course more pointed, and any material or element sitting right below that point easily absorb that heat, and melting and fusing of alloys and formation of intermetallics is possible. But while doing all this, the most important um, uh, entity is thermocouple, measuring temperature. You've seen all about the different furnaces, and how do you measure these temperatures? Just as you have different heating elements to produce different ranges of temperatures, we also have, or we also need, there's no single thermocouple that can measure all the way from the lowest temperature. Remember, temperature measurement that doesn't mean that it's all the way from room temperature to the highest temperature. Highest temperature is what? We're talking about 0 degrees centigrade to 3000 degrees centigrade. In a similar way, measuring low temperatures, liquid nitrogen temperature is 77 Kelvin. Liquid helium temperature is 4.2 Kelvin, right? And today we are able to achieve millikelvin temperature. So you're looking at going down all the way to minus 272 degrees centigrade and below. So there is again no single solution to measure temperatures. So that's where thermocouples, again, thermocouples in the form of two metals attached and to form a junction, or thermocouples in the form of mostly semiconductor diode thermocouple. Semiconductor diode thermocouples are used typically for low temperature measurements. So let's look at the concept of thermocouples. If you look at a thermocouple looks typically like this. It's one of the most frequently used uh, methods to measure temperatures with an electrical output signal in a very accurate way. So it operates in this fashion. You need two dissimilar metals, two metals that are not the same, and you form a junction like this. You braze them together. It's called brazing. And then when you heat this junction up, you start seeing a voltage generated. Because we are using two dissimilar metals, you'll have these two metals having two different work functions. And that's a key for making a thermocouple. The work functions of um, any two metals is different, of course. So that's the reason why we start with two dissimilar metals, so that the current flow in each of those arms or legs is different when the junction is heated, and that results in a voltage being developed there. Okay. So you need different thermocouples depending on the temperature range of measurement, about the required accuracy, and you also need to take into consideration the chemical resistance issues, because there are some thermocouples that are not, you cannot expose them to uh, chemical environment during the preparation process. The material itself may be emanating some toxic gases that might affect the performance of the thermocouple. Abrasion or vibration resistance is another important property that you need to consider. One is to properly install, because these thermocouples are always need to extend them from the furnace endpoint to the uh, measuring meters, that is typically an old meter. So you need to take care of those kind of installations. What the suitable wires have to be used. There are also thermal conduction requirements. So way back in 1821, nearly 200 years back, Seeberg observed the existence of an electromotive force at the junction formed between two dissimilar metals. Uh, Now Seeberg effectively saw a thermo EFM being generated when two dissimilar metals are attached or braced together. So it's actually the combined results of two other phenomena, namely Thomson and Peltier effects. The Thomson observed the existence of an EMF, electromotive force, due to the contact of two dissimilar metals at the junction temperature. Peltier also observed that a delta T along a conductor is observed in a circuit. The delta T along the conductors in a circuit can generate an EMF. In fact, Peltier effect is the reverse of Seeberg effect. Delta T can generate an EMF, and an EMF can generate a delta T. So today it's all about Peltier refrigeration. The Thomson effect is normally much smaller compared to the Peltier effect. This is a small animation to show that when you have two dissimilar metals having two different work functions, that is important. The electron flow in both the arms is different, and that is the reason why you get a definite uh, change in EMF, or a significant EMF is produced. This is not possible if both the arms are made of a single element. Like you can't have copper, copper, aluminum, aluminum, or gold, gold there. You need to have two dissimilar metals to produce that electromotive force. So if you look at material EMFs versus temperature, what you see on the y-axis is the positive and negative scales also. Positive EMF and negative EMF can be generated. Chromal, iron, copper, platinum, rhodium is an alloy. All these generate positive EMF, so many microvolts typically. And alumal and constantan, they produce negative EMF. Now, if you look at thermocouple materials versus electromotive forces, all these nomenclatures, the T, J, K, E, C, R, S, these are different names given to indicate or describe the type of thermocouples. These are called types. Types T, J, K are most commonly used thermocouples. You see that the T1, J, and K, the most commonly used thermocouples. What are their compositions? What they're made of? We'll see now. Okay. You see, the temperatures can range all the way from 0 to 2,500 degrees centigrade. And you see the EMFs generated, very low EMFs to a few EMFs of few tens of millivolts. And such EMFs are you can easily read using millivolt meters. Let's look at different types of thermocouples now. The most common type, you've seen that the most common types are TJK, and we start with the K-type thermocouple, which is made of uh, nickel chromium and nickel aluminum alloy, right? Two different, uh, so these two wires are two different alloys of nickel chromium, and the other one is nickel aluminum. It's a most common type of thermocouple. It is accurate, it is reliable, and it also covers a wide temperature range. It usually works in most applications as these thermocouples are nickel based and they exhibit good corrosion resistant. Nickel based alloys are good corrosion resistant alloys. They don't get corroded easily. As you can see, the temperature range is from minus 270 to 1260 degrees centigrade. That's a wide temperature range, all the way from very low temperatures to reasonably high temperatures. Right? Accuracy of measurement is plus or minus 2.2 degrees centigrade, which looks good. So typically, a thermocouple is it looks like that, and this part is outside the furnace of the measuring space, and this is sitting inside the hot zone, which is also insulated. So look at that. It looks like that, right? The inside of it. And what you normally see is just two leads which you connected to um, the voltmeter. So this part is what you're seeing there, this one, and this goes and sits inside the furnace, and on the other side you just connect these positive and negative terminals to the voltmeter. You have type J, the thermocouple. Again, another commonly used thermocouple. This is iron constant and thermocouple. It is composed of a positive wire, which is iron, and a negative wire, which is approximately 45% of nickel and 55% of copper. So one is a single element, the other one is again an alloy. Type J is also very common. It has a smaller temperature range on the high temperature side, and a shorter lifespan at high temperatures than the K-type one. The low temperature range is similar to what you've seen in this case, 270, minus 270 degrees centigrade, but the high temperature range is little limited to less than 800 degrees centigrade. Accuracy is similar to what you've seen in the case of K-type thermocouple. The construction looks the same. You see that that's typically the two joined, or this is called brazing, brazed metals or alloys are concealed inside insulating rod like that, and which is, of course, should have a good thermal conductor. And you can also place the junction directly inside the heating zone, and these are the extended parts of the wires coming from the two thermocouples, and they're connected to the voltmeter. That's how a typical thermocouple looks like. Now you have the E-type thermocouple, type U thermocouple. This is nickel chromium and constant. And again, both the parts are alloys. So the positive wire consists of 90% of nickel and 10% of chromium, right? And the negative wire is made up of 95% of nickel and 2% aluminum, 2% of manganese and 1% silicon. It has stronger signal and higher accuracy than the K-type one. The temperature range is minus 270 to 870 degrees centigrade, and the accuracy is anywhere from 0.5 to it's plus or minus 0.5%, and in terms of uh, temperature accuracy, it's plus or minus 1.7 degrees. Then the type N thermocouple is nicrosyl and nickel. So type N shares the same accuracy and temperature limit as the type K thermocouple. The type N is slightly more expensive. It consists of nickel, chromium, silicon, and on one side. On the other side, you have Ni, silicon, and magnesium, right? In those ratios that I have shown there. It also is found useful, found to be suitable than type K, especially when it comes to the usage of this thermocouple in nuclear environments. Temperature range is minus 270 to 390 degrees centigrade. These are the accuracies given there. The type S thermocouple is again very commonly used thermocouple. This is platinum rhodium and platinum and platinum rhodium. So the positive leg is approximately made up of 90% of platinum and 10% of rhodium. These are expensive thermocouples, but they're very robust. And the negative wire is made up of 94% platinum and 6% rhodium. That's where you create that little difference in the work functions. So it's used in very high temperature applications. Biotech and pharmaceutical industries require high temperature heatings. There's a lot of chemical environment, and you don't want the thermocouple to chemically get reacted to the gases that evolve during the process. And platinum, rhodium are two corrosion resistant materials or elements which which are very stable in different gas environments. Temperature range is from minus 50 degrees centigrade to 1480 degrees centigrade, and that's the accuracy. Then you have the R-type thermocouple, which is a combination of platinum, rhodium, and platinum again. The positive wire consists of 87% platinum, 13% rhodium, and the negative wire is a complete platinum wire. Yeah. And it's used in very high temperature applications. It has a higher percentage of rhodium than the type S thermocouple, which makes it more expensive. And but the accuracy and stability are very good always when it comes to platinum and platinum rhodium thermocouples. The high temperature detection range is a little more than what you've seen for the other thermocouples, but the low temperature limit is minus 50 degrees centigrade, and you can see the accuracy given here. Then we have the type B thermocouple. This is platinum rhodium and platinum rhodium. These are different compositions. So the positive wire is approximately 70% of platinum and 30% of rhodium, and the negative wire is approximately of 94% platinum and 6% rhodium. Now, the B-type thermocouple has the highest temperature limit. It can measure up to 1700 degrees centigrade. So it's quite useful going all the way from canthal to nichrome to silicon carbide heating furnaces. And to some extent, even supercanthal heating furnaces can be, temperatures can be measured using this thermocouple. See, when we're talking about alloys, making one of the legs or wires of the thermocouples, now you know how to make those alloys using the arc melting unit. That means you need to have a combination. For example, one of the legs or wires has to have 70% of platinum and 30% of rhodium. So, and the other one, 94% platinum and 6% rhodium. So you know that now using arc melting furnace, you can easily um, make these compositions. But the problem comes when you have these two elements that have different vapor pressures. In the sense that one element has a higher melting point compared to the other one. So what do you do in that case? You may not end up getting the exact 70-30 here, 94-6 there. But this is what is required to make a type B thermocouple for accurate measurements. If this compositional percentage, if it changes, the temperature range also will start changing. So arc melting, that's why it plays a very crucial role in making these alloys, and making these alloys with absolutely accurate uh, compositional ranges is always important. Think about what happens if one element has a lower melting point than the other one. Uh, what do you do in that case? Just keep thinking about it. So these thermocouples are now nicely standardized, and just as you can identify resistors, you can also there's also color coding for these thermocouples, and you can easily identify uh, you know uh, from the color coding of these thermocouples. For example, the T-type thermocouple is a maroon color. The J-type is typically it's a yellow colored one. So the moment you see a J-type thermocouple, you should recognize it as a J-type thermocouple, and you're seeing a J-type thermocouple is nothing but ion constant, and right. Um, and then a K-type thermocouple is blue in color, um, and you also have K-type multiple strand thermocouple also available in two different forms. And there's also a K-type fiberglass. It's called KBB type thermocouple. There's a K-type multi-strand shielded thermocouple. So there are different ways depending on the usage. These thermocouples are available. Again, if you go through the standard tables of the handbook of thermocouples, you get all the information about the exact measuring range for a given type. Even in K type, you're seeing already 4 different types in terms of multiple strands here, multi-stranded shielding here, and fiberglass here. So I want you to go through the handbook of thermocouples and try to find out what are the subtle differences in all these different uh, forms of the same K-type thermocouple, which is different from T and J. There's also a sheet material which is required. See, this is a metal sheet. That's a thermocouple conductors. That's a thermocouple measuring point. That's where I said two thermocouples are. You don't call it normally welding. There, you brace them, right? Welding means you normally use a different another element. So we are not using a third element here. It is a combination of these two dissimilar metals, A and B. So you heat them to very high temperatures, and so you're forming a junction there of the AB elements itself without uh, bringing another element like lead or indium that is normally used in the process of soldering. So this should not be called as soldering. This is called brazing. So that's how the interior, if you look at the cross section, that's how typically a thermocouple assembly looks like. These two are solidly embedded, and the junction is there to, you know, that's a measuring point. There's a ceramic insulation around it, and of course, this is of course the metal sheet, right? So when you have a metal sheet, this is the measuring elements forming a junction there. There has to be a ceramic insulation. So if you look at the materials, anything when we say refractory oxide or a refractory element, that means you're dealing with a high temperature element or a compound. Tungsten, molybdenum, tungsten oxide, molybdenum oxide, rhenium. These are all high melting point elements and compounds. So refractory oxide recrystallization process, uh, and alumina is one of the very effective material that is used as a sheet material, ceramic insulation. Maximum continuous temperature can be as high as 1750 degrees centigrade, and it's a good choice for rare metal thermocouples. It's a good resistance to. It has good resistance to chemical attacks also. What are all the applications there? Forging iron and steel, incinerators, carburizing, and hardening in heat treatment, and continuous furnaces that go on for months together. Silicon carbide um, can go or take up to 1500 degrees centigrade. The notable points here are the good level of protection even in severe conditions. It's good resistance to reasonable levels of thermal shock. Now again, forging iron, steel, and various other applications, this type of material is used. Mullite, impervious mullite, maximum continuous temperature could be 1600 degrees centigrade. Again, a good choice for rare metal thermocouples under severe conditions. When you have sulfurous and carbonaceous atmospheres, mullite is quite resistant to these atmospheres, which is quite good. Again, uh, it's a good system for continuous furnaces. Stainless steel 2520. The temperature is maximum continuous temperature is not very high, limited to 1150 degrees centigrade, and the notable point here is it resists corrosion even at elevated temperatures. Can be used in sulfurous atmospheres. This is good for heat treatment, annealing, and in many chemical processes. If you continue this, you have Inconel. Inconel is there, and corresponding data is given there. You have chrome iron, and you have nichrobel. All these are very common types of sheet metal materials used for various maximum continuous temperature ranges and various applications. So this is one of the biggest challenges is using thermocouples, because some of the furnaces are on for a long period of time. I told you about heat treatment typically for uh, you know uh, 3 to 4 days continuously. So the heating elements have to be intact. At the same time, your thermocouple has to withstand, and it should not, especially when the junction is broken, the temperature reading is gone. So you need to have thermocouples that can sustain for longer periods of measuring times. Yeah, a typical, again, typical pictures of thermocouples are available in various shapes, sizes, and forms. No, that's how a furnace thermocouple looks like. This goes inside. If you have a box furnace, this part goes inside the furnace, and the or from it sits on the top, and you take your electrical connections to the top, or you have another socket which is plugged here from where the wires are taken and connected to the electric meters. No, here it's this to the jacks which can be connected to the measuring voltmeter. So there are various types depending on the requirement. This is just a plug-in type thermocouple, thermocouple with you know, see that they're different. Uh, it has really evolved in a big way. Yeah, typical thermocouples from this company. I've taken pictures from their website. So again, thermocouple is a very commonly used thermocouple for furnaces. Uh, a thermocouple that is connected to in the thin film growth. Typically, you have physical vapor deposition, chemical vapor deposition growth. There, you have a heater, and because the chamber is all closed and evacuated, you can only plug in uh, the thermocouple to a point from where you know the rest of the thermocouple is used for measuring the temperature inside the system. And there are also it all depends on the requirement. There are also thermocouples that are movable. You connect this long wire to a meter, and you have several places where you want to measure the temperature. So you can just carry it with your hand, and also one hand your measuring meter, and you can transfer the thermocouple along with the measuring meter from one point to the other point. Yeah. So coming back to, so you also need a thermocouple here. The arc melting concept that I mentioned about, you see, when you, one thing that you should realize is, I said, this is a copper hearth, right? This is a copper hearth on which I keep, let's say, um, I want to make platinum rhodium, right? I have a small piece of platinum, small piece of rhodium, and you need to know everything about their vapor pressures, right? If one element is vaporizing faster than the other one, so you need to compensate for the loss caused by the first element evaporating faster. So that means we need to do some calculations based on the atomic concentrations, atomic weights of, and molar concentrations of these two elements. And there, there might be, in most of the cases where the vapor pressures are different, you have to have one of the elements in excess of concentration, either in weight percent or atom percent. Otherwise, your final composition will not be the required one. You might think that by taking 60-40 of element A and element B by weight percent, you melt them, you might think that you end up getting 60-40 ratio of the melt. No, it need not happen. Because if the vapor pressures are largely different, the final composition, the percentage, atom percentage or weight percentage of the final composition will be completely different from what you started with. That's where you need to compensate. The second point is, this is a mobile electrode. This whole thing is evacuated. This is a moving electrode. I bring in close to the point where the melting happens. The two ingots, two elements A and B are there. and the whole chamber is evacuated. I have argon gas inside. The moment I bring this electrode, this is also an electrode. Your second electrode is copper, on which the whole melting process happens. The moment you bring this one close to within few millimeters, centimeters, you start seeing a powerful plasma generated there, and that plasma uh, generates a lot of heat, and the elements in these, you know, those points there, those depressions, start absorbing that heat, and they'll start melting. Okay. Now, so this is one of the electrodes. This is one of the electrodes. The top one is another electrode, right? But don't you think that when this temperature is, you can even melt an element that is 2000 degrees centigrade, an element that has a melting point of 2000 degrees centigrade, it melts. But don't you think copper will start reacting with that melt? Copper is one electrode. The whole action is happening. It's just that I don't want the molten alloy to flow out. I can't melt these two elements on a flat surface. That's why I create a small depression. There's several of them. This is just to contain the molten liquid inside. And once it solidifies, you get a piece of the alloy. That's a different case. But what makes you think that the copper itself is not reacting with this, right? That should be the question that you should have in your mind. Actually, copper doesn't, should not react because if platinum, when you're making a platinum rhodium alloy, if copper is also contributing to that composition, then you're not talking about only platinum rhodium alloy composition. You also have platinum rhodium copper. And this is called the copper hearth. The copper hearth is used for multiple uses. You know, the beautiful thing about why copper doesn't melt here, there is a continuous water circulation around this copper hearth. Water is always circulated at about 20 degrees centigrade. So the surface is always cooled rapidly, right? The surface is always at 20 degrees centigrade. So whatever heat is generated during the process of the alloy formation, that heat is continuously taken away by circulating cold water, right? So that's a beautiful way of keeping the copper hearth intact. It won't melt and react with the alloy that uh, you need to make there, right? Okay, then I'll stop there, and I'll see you in the next class.